Yeah. Up to yesterday, we discussed about the elasticity, right? If you see elasticity, stress and strain, the steel has the more elasticity. If you think that, we think that the rubber has the more elasticity because rubber requires the less force for deformation, right? If you're stretching the rubber, it will become bigger in size. When you leave that rubber, what happens? It does not come to the original position initially, how it looked like. But if you take a steel, right, the force required is maximum to bend or to give stress. But once it released, it comes to the original position as like previous. So here the elasticity means the deformation, then how it will formed after deformation, right? So which one has the more elasticity means rubber or a steel. The steel has the more elasticity because it comes to the original position as like, right? That nothing but the elasticity that is used by young modular stiffness pressure to maintain the change in pressure, change in stress and strain, right? If you are stretching the spring, what happened that is extra force is required. So that is stretched, right? When you are leaving it, it goes to the original position. So steel has more elasticity than rubber. When come to the pressure, pressure is nothing but force by area. You know that when the area is less, because in the denominator, automatically the pressure will be high, right? Because indirectly proportional. You can see here in this case, right? The piston is pushing down. What happened? The area gets reduces. When the area get reduces, automatically the pressure is increasing. You see in the second case, what happened? The pressure is minimum. That force is the minimum. What happened? The area will be more, so the pressure will be low. So you have to understand when the area is low, pressure will be high. When the area is more, automatically the pressure will be low. You can see the needle. The needle have the sharp, that is a lower area. The area is lower, so it is having a high pressure, right? So the atmospheric pressure is calculated by means of the instrument barometer. Barometer is used to find the atmospheric pressure. It is also asked in some MCQs. When come to the properties of matter, you are going to see flotation, loss, and surface tension, right? The one thing you have to remember in floating and loss, the weight of the body and the Buoyant force, right? Weight of the body and another one is the Buoyant force. A body floats in a liquid when the weight of the body is equal to the weight of the liquid displaced by it, right? There is nothing but the Buoyant force. The body is going to displace the equal weight of the liquid. So if it is 1 kg, the 1 kg equivalent water is going to disperse out. That is nothing but the Buoyant's law. You will see in the next slide, Buoyant's law. Here you can see that the weight of the body is equal to the weight of the displaced liquid. It is nothing but the body is going to float. If the weight of the body is greater than the Buoyant force, what happens? That is the density of the liquid. It is going to sink, right? When the Buoyant force is greater, right, then the weight of the body, it will be rises, right? You can see here it's based upon the density. They are saying, see, the density of the water is 1, the density of the ice is 0.9. So the density of ice is less than the water. If it is less than the water, what happens? The ice is going to float. The ice is going to float here. You see in the surface tension is nothing but it's in between the water molecules, right? That is called the cohesive force. You see that it is like a layer. This is called as a cohesive force due to that the water is have a high density. Actually, the liquid surface behaves like a elastic sheet like this, right? So this is concept of the cohesive force, right? You see that here the density of the cockroach is less than the density of the liquid. So what happened? The cockroach is going to float. or walk on the water itself. So the insects can walk on the water because the density of an object is less than the density of the liquid, right? Yeah. Next, come to the Pascal's law. Yeah. What is Pascal's law? The pressure applied at one point of a confined fluid is transmitted equally and undiminished in all directions. That means you can see that this is a pressure transmitted equally in the fluids. This is the all the directions. This pressure applied at one point of a confined fluid is transmitted equally and undiminished in all the directions. For example, you can see hydraulic brake lift, the small force lift the heavy car. You can see that we are applying a small force. Pressure is nothing but force by area. We seen in the previous, right? Pressure is nothing but force by area. When the area is minimum, what happened? The pressure is going to be the maximum, right? Here the area is minimum. We are going to apply only a less force, right? What happened due to that? Like some fluid is there inside that, it is going to pressure is down. What happened? It is going to give more force in the more area. So it is going to lift the car up, right? So what do you understand? By using a less force in the less area, the pressure will be more. When the pressure will be more, it is equivalent to the another area that is higher area, then higher force will be there. That is P1 is nothing but F1 into A. There is a small force is applied. Here you can develop a large force by using that one, right? It is one of the important of this Pascal's law, where hydraulic braking and lifting, you can see that pressure, right? The small force on a small area produces a large force on a large area. So works only on confined liquids only it is work. Where you can see the application means hydraulic brakes, hydraulic lift, hydraulic press, everything you can see. It applies to liquid only. The pressure is same in all the directions. You have to keep it in mind, right? When come to the Archimedes principle, right? I already told that the Bionon force is equal to the weight of the equal displacement. So suppose you are going to place some wooden box inside a water, in a jar of water. What happens? If you put with the weight, that weight of the wooden box, the equivalent liquid is going to displace out, right? Then what happens means it is going to float. It is going to float. That is nothing but the Bionon force. A body wholly or partially immersed in a liquid, right, experiences an upward force equal to the weight of the liquid displaced, right? So experienced a upward force. That upward force is nothing but Bionon force, right? Actually, the weight of an object is going to pulling down, the Bionon force is going to rising up. That equivalent liquid is displaced out. In the same phenomenon, our boats, everything is functioning. You can see that this is the weight of the ship, right? It is having a Bionon force. The Bionon force is making to float, making the boat to float, and the right here, what we can say, the weight of the ship is equal to the Bionon of the Bionon force of the ship, right? The weight of the force making it to gravity, or as you got to say, pulling it down, the Bionon force is making it to rise. You can see the explanation here. This is a submarine. You can see the submarine is also inside the water and it can flow above the water also. So how they are changing this thing, you can see that here in this case, when the Bionon force is greater than the submarine weight, what happened? It is seen in the surface area. It is seen in the surface area. If the weight of the submarine is greater than the Bionon force, what happened? It is going to sink. It is going to go inside the water. So based on this condition, this Bionon principle and the Archimedes Bionon force and Archimedes principle, our ship and submarine is functioning, right? So what is here? You understand the upward force is nothing but the Bionon force, right? If the body is going to float, it is going to disperse the equivalent weight of the liquid, right? So you can see that in Pascal, we seen about the pressure transmission. In Archimedes principle, that is nothing but the Byron force. You have to keep it in mind because in sometimes in examination ask the Pascal's law where you are using, it is about pressure transmission. Whenever you see Pascal's law, you have to remember the car is lifted up with a small force, right? That is nothing but the Pascal's law. Whenever you see the Archimedes principle, you have to remember that you have to remember that the ship is going to float by means of the buoyant force. The buoyant force is the upward force, and the weight of the body is going to act in the opposite direction. Because of the Archimedes principle, the equivalent weight of the body is going to disperse out, right? That is nothing but the Archimedes principle. So it's based on that our submarine and the ship is functioning, right? Okay. I'll ask one question. Hydraulic brakes work on which principle, Ajit?
ஹைட்ராலிக் பிரேக் வந்து பாஸ்கல் லா.
Hydraulic brakes refers to the Pascal law. So Byron force is equal to weight of an object, density of the fluid, volume of an object, weight of the displaced fluid.
Weight of the displaced fluid.
Yes. Next, we have to see this one. I think this is the same slide, right? Same slide we discussed already. Yeah. Come to the capillarity. Right? The capillarity is nothing but the action and the gravity. Capillarity is a phenomenon by which the liquid rises or falls in a narrow tube due to the surface tension and adhesive and cohesive force. We can see that in the previous slide, we can see the cohesive force. The cohesive force is in between the liquids, right? The liquid molecules that is formed one layer, like in you can see in the sea, because all the molecules are density and tightly packed one to one. So it is forming a cohesive force, right? There is another force is nothing but adhesive force. The adhesive force is between the liquid and the solid. Liquid and the solid. In this case, if there is a narrow tube that is between the wall of the narrow tube and the liquid, that is nothing but the adhesive force, right? The cohesive force is nothing but the liquid and liquid attraction. Cohesive force is nothing but liquid to liquid attraction. The adhesive force is nothing but the solid and the liquid attraction, or you can say that the wall of the tube and the liquid attraction. So what happens if the adhesive force is more? What happens? The water is going to, or the fluid is going to rise in the tube. The fluid is going to rise in the tube when the adhesive force is greater than the cohesive force. If the cohesive force is more, what is happen? It is going to fall. The water is going to this direction, downward direction. If adhesive force is more, its work against the gravity, it moves up, right? When it moves up, adhesive force will be more. When moves down, the cohesive force will be more, right? Based on the surface tension. So what do you have to remember? The cohesive force is nothing but the liquid to liquid attraction. Then adhesive force is nothing but the liquid to solid reaction or liquid to this wall tube attraction, right? So adhesive force is more means what happened? The liquid going to rise up. If the cohesive force more means the liquid going to falls down, right? So I have to keep that in mind. Rises means adhesion is greater than cohesion. For example, water in a glass tube. Mercury, if you see mercury in a glass tube, it is false, right? So here, cohesive force is more than the adhesion. You can see some examples how it is going to up, right? The liquid is going to up, oil in wick and sap plums in tree. It is going to, the water is going to flow from the ground to the trees directly. So bottling paper, this is between the action and the gravity. So in the action and the gravity, we have two things, adhesive and cohesive. Adhesive is liquid and solid. Cohesive means liquid to liquid, right? If adhesive is more, it is going to rise up. The cohesive is more, it is going to fall. Let's come to the viscosity. Yeah, viscosity Yeah, you can see that viscosity is nothing but the internal resistance offered by a fluid to the flow of its layers. Right? It's nothing but the internal resistance. You have to keep it in mind. It is nothing but the fluid friction. It is nothing but the fluid friction. You can see if you are pouring a 1 liter of water in a bar, it takes only less minute. The same thing, 1 liter of honey is there. If you are pouring, it takes so much time because of the honey is having the high viscosity. Honey is having the high viscosity. Water is having the low viscosity. If you see engine oil, the viscosity gets decreases, right? That is the density, that friction gets decreases when it heated up. When it heated up. So what a viscosity? The viscosity of water is low. The viscosity of honey is very high. Viscosity is nothing but here the fluid friction. That is nothing but the internal resistance. Internal resistance of the liquid, you can say that is called viscosity, right? You can see here liquids. What happened? Liquids, actually the viscosity is gets lowered with the heat. When you are increasing the temperature, what happens? The viscosity is going to down. In the same thing, if you see in gases, if you are raising the temperature, what happens? The viscosity is going to rise. That is becomes a vapor, right? When you are heating up the gas, this is going to vapor only. The viscosity here you have to see that it is indirectly proportional in liquid. It is directly proportional in gases. When the temperature rises, what happens? The viscosity is going to fall. So, indirectly proportional in liquids. Here we see that the temperature rises in gases. What happens? The viscosity is also going higher. So, it is directly proportional in gases. You have to remember these things. Viscosity is nothing but the internal resistance. The viscosity of the water is low when compared to the honey, right? If you heat it up, what happens? The viscosity gets decreases actually. But if you see in a gaseous stage, the viscosity is also increases with the increase in the temperature. Because this may be twistly asked in the questions, to keep it in reminder. Next, to come to the important topic. Yeah, it is nothing but the Bernoulli's principle, right? See, for a fluid, the steady flow, the sum of pressure energy, you know that it is having a kinetic energy and potential energy. Kinetic energy means what? Kinetic energy is nothing but when the body is in motion, it is having some energy. For a traveling car, right? The ball is thrown at the sky, it is having some kinetic energy, right? Potential energy is nothing but it is ready for an action, but it is at stationary. For example, the water in the dam, you see that the water in the dam have the potential energy. If you open the dam, the energy is going to change to kinetic energy, right? So here you can see in Bernoulli's principle for a fluid streamline flow, right? The sum of pressure energy, that is kinetic energy, and potential energy per unit volume remains constant. It is always constant. The kinetic energy and potential energy is always remains constant. So you have to see when fluids faster, if it is used kinetic energy. When fluid becomes flow faster, it uses a kinetic energy. I already told kinetic energy is present in the motion, right? Uh, so its pressure energy decreases. So pressure energy is nothing but the potential energy. You see that I also already said water stored in the reservoir. Water stored in the reservoir, it have a large pressure and a large potential to flow, right? That is nothing but the pressure. The external pressure will be there, right? There is a huge water in the dam. If you are going to open the dam, all the water is going to flow. That is nothing but the pressure energy, right? The kinetic energy is means the body is under the motion, that is the kinetic energy. So here you see when you are applying a high pressure, what happens if it takes the started flow, it takes the kinetic energy, automatically the pressure is gets decreases, right? When the pressure is lower, automatically where speed is be higher due to the kinetic energy, right? So you see, what you understand in the Bernoulli's principle? The Bernoulli's principle, the fluid is idle, whether it is non-viscous. What is meant by non-viscous? We seen the viscosity previously. What is mean by non-viscous?
less resistance of
Yeah.
durability.
Yes. Non-viscous means it is not having any opposition or no internal resistance, right? So what happened? The flow is steady. What happened? It is flow is as long as in the streamline, right? So initially only the high pressure is required. When it starts in the kinetic energy, there is no pressure also. It's working fine in the tube-like structure. That is nothing but the Bernoulli's principle. You can see here for the examples of Bernoulli pressure, that is high speed is equal to the low pressure. That is a lift of airplane wing. You see that it is like a curve like structure. The what air flows in that, it is changed to low pressure and high pressure. What happened? High pressure is formed under the blade of an flight. The low pressure is formed at the top of the blade. It makes the flight to fly up, right? So this is the upward lift. The pressure above wing decreases. The pressure below wing is increases. So net out actually it moves means it is upward lift, right? So the low pressure is formed above the blade, the high pressure is formed below the blade. So what happened? It is going to climbing up, right? So in a narrow pipe, you already seen that a narrow pipe, the speed will be higher. Automatically, the pressure is going to down. The pressure is going to down in the narrow pipe, right? You can see the wind above the roof. It is formed due to low pressure, right? It pushes the roof upward. It pushes the because the high pressure is formed below the roof and low pressure is formed in the above the roof. What happened? The low pressure is formed above the roof and high pressure is formed below the roof. Automatically, the lift is going to happen. So it is it is automatically throw away the roof, right? So you can see in the atomizer as an example. Now the come to the important one, that is a surface tension. It is very interesting. You see why hot soup is tastier. You see, the water is not tastier if you are drinking, but hot soup is tastier. It is because of low surface tension spreads over the tank better. You see that? Because actually it is having high density. The water is having the density. The surface tension, you see that. Cold soup is having high surface tension, but it is not spread in the entire tank, right? This is nothing but a high surface tension. If you see hot, right, when it heated up, what happened? When you heat it up, there is low viscosity. What happened? It is going to spread all over the tank, right? So it's a better spread and more taste, right? That is why the reason the soup gets tastier because of the salt, everything is added. It is because of this surface tension. It is going to spread over the entire tank. But if it is soup is colder or somewhat, right, what happened? It is not going to spread over the entire tank. You see that if you use your water, if you make it heated up only, the surface tension is making a lower. Then only if you can see in a washing machine, there is a provision is provided for heating up the water. Why means in heating up the water only, it is low surface tension. It is going to spread on the entire cloths, right? So you have to remember this thing. This how it is changing for the low surface tension. Anyone is asking permission to enter. Wait a minute. Yes, I am. Okay. Okay. Next, come to the. Okay, I'll ask one question based on the Bernoulli's principle. Bernoulli's principle is based on the conservation of mass, momentum, energy, force. Hmm?
Energy. Energy.
Yeah. Bernoulli's principle is based on the energy conservation, right? Because speed and pressure that is based on the energy conservation. In a flowing liquid, pressure is minimum where? Velocity is minimum. When the velocity is maximum, height is maximum, and density is maximum. Again, I repeat the question. In a flowing fluid, here the fluid is going to, when the fluid is going to flow here, what happens? The pressure is minimum. Where the pressure is minimum. Here the high pressure is there, right? I told, right? Where here the low pressure will be there. When the pressure is minimum, where velocity is minimum, velocity is maximum, height is maximum, density is maximum.
velocity.
Yeah,
Maximum.
correct. Velocity is maximum. Velocity is nothing but the speed, right? You have to keep it in mind. Velocity is nothing but the speed. You can see at low pressure, there is a high speed. At low pressure, what happened? There is a high speed. What is asking? In a flowing fluid, the pressure is minimum. Pressure is minimum means low pressure. So low pressure is there, automatically the velocity is maximum. Here velocity is nothing but it's indicating the speed, the high speed. So you have to keep in mind at low pressure, the velocity is maximum, the speed is maximum. You have to remember that. So like this, questions might be asked. Yeah, next come to the heat topic. That the temperature. You know that heat is a form of energy that flows from hotter body to colder body due to the temperature difference. So we have three types of that Celsius, Fahrenheit, and Kelvin. Celsius is used in other countries, India like that. If you take in United States, we are using a Fahrenheit, right? That is commonly used as SI units. You can say that is a Kelvin, right? What is the difference between these three? Is nothing but we know that formula to convert the what to say Celsius to the Fahrenheit by using this formula. At what temperature these both are same, the Celsius and Fahrenheit is nothing but a minus 40 degree, right? The Kelvin is nothing but uh, Celsius plus 273 because it is nothing but the boiling point and the freezing point. Celsius is between 0 to I think 112 degree. This is nothing but 0 to 273 degree, right? That is just changes. There is a difference between Celsius, Fahrenheit, and then Kelvin. At what temperature Celsius and Fahrenheit are same, it is nothing but the finite. Minus 40. This is a conversion formula is nothing but F minus 32 by 9 to convert the Celsius to the Fahrenheit. And you can see this another expansion of water. Water contracts when heated from 0 degree to 4 degree. What happened? When you are increasing the temperature of the water, what happened? The density is going to rise up to 4 degrees Celsius, right? After 4 degrees Celsius, what happened? The density of an water is going to fall down. So when it is maximum at 4 degrees Celsius. We have to keep it in mind. This question might be also asked in the examination. The water contracts when heated from 0 to 4 degrees Celsius. That means at 4 degrees Celsius, the density of the water will be higher. The water will be higher. And this only you have to remember, it is a Celsius, Fahrenheit, and Kelvin difference. Yeah. Next, you can see that there are three modes of heat transfer: conduction, convection, and radiation. Conduction is nothing but heat through solids. That is nothing but metal rod. Right? This is the metal rod. So what happened? The heat is through the solid is nothing but the conduction. When you see the convection, there is the movement of particle or the fluid in a jar, right? So what is the boiling water? This boiling water is nothing but the heated up in the down. It is nothing but the convection. Then radiation is nothing but sun's heat. Sun, how you feel when you go out during the sunny season, the heat through electromagnetic waves. Through electromagnetic waves, that is nothing but the radiation. So you have to, there are three parts. Conduction is nothing but in between the solid or metals happening vibration. Convection is nothing but when you are heating up the fluids or some particles, that is a boiling water, that is nothing but the convection. Radiation means it is coming from the electromagnetic waves. That is nothing but the radiation. You need Kirchhoff's law. What is Kirchhoff's law? We have the two laws, Kirchhoff's current law and Kirchhoff's voltage law. In a closed circuit, what happened? The entering is equal to the leaving, right? How much it is entering the body and how much is leaving the body, both are same. That is nothing but the Kirchhoff's law based upon the electrical. Here you can see a radiation. The black is nothing but a good observer, right? What happened? The good observers are the good emitters. I say that inward, how much it is flowing, it is going to out also the same, right? That is a inward, good observer, good emitter. This is nothing but the Kirchhoff's law, right? The entering is equal to the leaving. The sum of all entering, the algebraic sum of all the entering is equal to the algebraic sum of all the leaving. This is nothing but the Kirchhoff's law. You can see that there is a good observers or good emitters. So black surfaces heating up fast and cooling down fast, right? How much fast they are heating up, the same way it is cooling up also. We can see in sunny season, sunny time, what happens, the temperature is gets increases automatically, right? Here in the cooling season also, it's easily gets cooled, right? Yeah. Let's come to the specific heat capacity. The specific heat capacity, I think that heat required, how much heat they required to rise a temperature of a unit mass by 1 degree Celsius. If you are making it to rise the temperature to 1 degree Celsius, that is nothing but specific heat capacity. That is heat needed to rise temperature to make a 1 degree Celsius. That is Q is equal to MC change in temperature. Water has high specific heat. What happened? It's a moderate climate. You can see very high specific heat used as a coolant in engines. Water is used in a coolant. If you in the all the engines, water is used as a coolant in engine. You can see here that is a low specific heat sand. That means in sunny season, the sand gets heated up quickly, right? After in the night, it's cooled up very fastly. So it is having the low specific heat. It is nothing but the low specific heat. That means it can easily absorb the heat also. It is easily absorb the cold also, right? That is nothing but the low specific heat. You can see here. So water is used as a coolant, right? That is because of very high specific heat. Let's come to the latent heat. Latent heat is nothing but heat absorbed or released during the change of state without temperature change. Without temperature. That means the temperature is maintained constant. Heat absorbed and heat released during the change of state is nothing but the latent heat. That means fusion. Fusion state means what? The solid is going to convert into a liquid. For example, the ice cube is there. If you are going to heat the ice cube, what happen? It is going to make us a water. It is going to in the liquid state, right? The next state is the vaporization state. Vaporization state, what is happening? First stage is a melting stage, right? That is water is going to be, ice cube is going to melt down to water. In the next stage, again, if you heat it up, what happens? The water is going to evaporate. That is vaporization. That is liquid to gas stage. That is nothing but the boiling, right? So there is vaporization. So you have to remember these things. This is see that the boiling steam burns is greater than the boiling water burns. So boiling water, it is just only, it does not burn. What happen? If you see in the 100 degrees steam, what happen? It makes wounded, right? It makes the skin to burn easily. So you have to remember, steam burns are greater than the boiling water, even though the temperatures are same. It is nothing but latent heat of vaporization. So here in the boiling stage, it going the gas, that is nothing but the steam. The steam is very dangerous when compared to the boiling. Yeah, next come to the heat engines, or you can say this Carnot engine. Okay. right? You can see here the heat engine, the practically no machine will provide 100% efficiency, but this is a theoretical case. This Carnot engine is going to uh, this is efficiency is maximum. Which machine heat engine is giving the efficiency is maximum in the heat engines. You can see here hot source, hot reservoir, and this one is the cold reservoir, right? Hot reservoir is going to supply heat, right? Here the working substance is nothing but the gas steam is used to convert that what the hot energy to a work done here. After the work is completed, right, the water absorbs gets rejected. That is in the cold reservoir. QC, right? QC is nothing but the cold. QH is nothing but the heat order, and that is hot reservoir. How it is working? Heat is taken from the hot source, and the part of heat is converted into work. That is using a steam, and this part of work is converted into work. The remaining heat is rejected to cold sink. This process is repeated cyclically. That is why the Carnot engine is current. I already told the ideal engine. Ideal engine is nothing but it's a lossless engine. They are not taking any losses here. So it is not a practical engine, it is a theoretical engine. That is ideal means there is no losses. Because whenever we can test anything, we can go with the ideal case first. Then only we come to the with the losses. So here the efficiency is depends upon the temperature of source and the temperature of sink. The sink is nothing but the cold here. This is nothing but the hot reservoir. Now you can see that efficiency. Efficiency is nothing but 1 minus Tc. That is the temperature of cold. This is the temperature of heat. Efficiency is always less than 1. Efficiency is always less than 1. If it is equivalent to 1, it is nothing but 100%. You can see here, right? That is between pressure and the velocity. Pressure and the velocity. It is a Carnot cycle. Isothermal expansion is nothing but the heat absorbed. Heat absorbed. So adiabatic expansion is nothing but the heat temperature fall to the cold temperature. So adiabatic expansion, you have to remember because maybe it's the expand the heat. What to say? The temperature reduces from heat to cold. Which expansion that one? That is nothing but the adiabatic expansion. That the heat temperature falls down to cold temperature. That is nothing but the adiabatic expansion. When the cold temperature, it is going to rise to the high temperature. That is nothing but the adiabatic compression. Compression means lower to higher. That is cold to hot temperature. That is nothing but the adiabatic compression. When you see isothermal compression, isothermal compression is nothing but this wasted water. That is right after engine. What happened? That wasted heat is going to fall down. Right. That is in the cold sink. That is nothing but the isothermal compression. That is going to reject the exhaust of water. Exhaust of water is nothing but isothermal compression. So in this Carnot engine cycle, that is the pressure and volume. There are 4 types: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Right? This absorbs the heat is nothing but isothermal expansion. Leaving the heat is nothing but isothermal compression. From heat to cold is nothing but adiabatic expansion. From cold to heat is nothing but the adiabatic compression. Right? You see here that the cooking utensils, you can see it in your home, right? There is a bottom, you can see there is a surface, it's blackened because it blackened surface absorbs heat. The black is a great absorber of heat. We've seen in the previous slides also. So this one you see that it's a shiny part, right? The shiny part, what happened? It reflects the heat. It absorbs the heat. So what happened? It's quickly heating the thing. Water it heated up right quickly, but it is take some time because of this radiation. So to absorb more heat, right? Which one is used? You have to use a blackened surface. You have to use a blackened surface. So that is nothing but heat and thermodynamics. And one more thing, we right? Which law is used in the first law of thermodynamics? This is very important law. I will remember as we studied a physics.
Energy neither be created nor be destroyed.
Good. Energy is neither be created nor be destroyed. It can only be transformed. It can be only be transformed. That is the first law of thermodynamics. What is the zeroth law of thermodynamics? It is the basic of temperature measurement. If A is in the thermal equilibrium with B and B with C and A with C, that is nothing but temperature measurement. You have to use the zeroth law of thermodynamics, right? That means if A is in the thermal equilibrium with B, similarly B with C, C with D, and A with C, like that, right? That is the stages of zeroth law of thermodynamics. Why I am saying means in the question they might be asked, which law gives the definition of temperature? You have to keep it in mind. Zeroth law only gives the definition of temperature. Zeroth law, right? And then heat engine efficiency can never be 50%, 70%, 100%, 80%. Efficiency. Efficiency is 100%.
Never 100%.
It is not 100%, yeah. Uh, can never be 100% because it gets wasted up, right? So there is not heated up. So it is not 100%. And come to the topic, next topic. Which engine has the maximum efficiency? A steam engine, petrol engine, diesel engine, Carnot engine. Hello?
Don't know, sir.
No, you've seen in the previous, right? Adiabatic process, adiabatic compression, everything, right? Which engine has the maximum efficiency means it is not 100%, it is less than the 100%. That is nothing but the Carnot engine, right? What engine you see in previous? The Carnot engine only gives the maximum efficiency. Carnot engine only gives the maximum efficiency. Okay, the efficiency of Carnot engine depends on working substance, pressure, temperature of source and sink, volume of gas. How the Carnot engine?
Temperature of resource sensing.
Yeah, temperature of source and sink. You can see that there is hot reservoir and then cold sink, right? Based on the temperature only, the work is done, carried out, right? You have to remember that. That is called Carnot engine. Carnot engine only, the efficiency is maximum. I'm not saying 100%. Maximum efficiency can be done through Carnot engine only, right? But you are not maintaining 100%, but it is maximum efficiency is maintained. It is between temperature of source and sink because it might be asked in exams. Okay, let's come to the sound and waves, right? Sound and waves, we have two types, that is longitudinal and one is transverse, but we see what is longitudinal. Longitudinal wave is one which particles of the medium, that is, there are so many particles are there, the particles of the medium vibrate parallel to the direction of the wave propagation. It is always parallel to the direction of wave propagation. It consists of compression, right? It's compressed. It consists of compression and rarefactions. It's need a material medium. It's need a medium. If you want to transfer to what to say to travel, it needs a longitudinal waves requires a medium. So it cannot be polarized. So this is the characters and features of these longitudinal waves. For example, sound waves in air, right? Sound waves in air, it is nothing but the longitudinal waves. Why the sound waves in air? Sound requires a medium to travel. You can see here this, the speed of sound. The sound is faster in the solids. If it is a steely part that is covered entirely by steel, the sound is maximum, fastest, and somewhat lower in the liquid, and somewhat lower in the gases. There is zero. Sound is speed is the sound of speed is zero in the vacuum. You cannot hear at all. That is 0 meter per second. So you have to remember it is fast in steel. The sound is maximum in steel only. So what happened? The longitudinal sound waves in air It requires a medium, whether it is air is also a medium. So it's 340 meter per second, the sound it takes in the air. So longitudinal waves requires a medium, right? Speed depends upon elasticity and density. Density of the medium. The density of the medium is also dependent. It's usually travels fast in solid state. You can see the steel is a solid. So it's fast in the solid state, right? When compared to liquid and gases, the sound travels very faster in the solid state, right? When come to the transverse is one, its particles vibrate perpendicular. You can see that it is like a oscillation. It's like a 90 degree. Here it's also 90 degree. It's also 90 degree. It is also 90 degree. Here the wave direction is like that, right? So it is perpendicular. The particles vibrate perpendicular to the direction of wave propagation is nothing but the transverse. You have to keep in mind, right? Here the particles vibrate perpendicular to this one. Here the particles vibrate parallel to the wave direction. It is, well, in this case, it is going to vibrate parallel. That is nothing but longitudinal wave. If it is working perpendicularly, like a sinusoidal wave, you can see it is perpendicular to the wave direction. It is nothing but the transverse. So this is the difference. This is longitudinal means parallel, transverse means perpendicular. Keep it in mind. Right? It does not require any medium. It does not require any medium. I already told it cannot be polarized. Right? Here it will be polarized. That means you have to filter it. Right? It can be polarized. The examples of transverse wave, water surface waves, right? Light waves. Longitudinal, you take it here, sound waves as an example. Here, transverse here is nothing but it's the light waves and the water surface waves and the waves on a stretched string. These are the examples of transverse waves. Stretched string means you can see the guitar, like, right? It's vibrate. If you vibrate, what happens? There is a vibration will be there. Right? That is nothing but the waves on a stretched string, right? So light waves is nothing but the electromagnetic waves. These are all come under the transverse waves. So light waves are transverse waves. It keep in mind the transverse show polarization. Yeah, this thing is seen already. The sound travels faster in the steel when compared to water, air, and all. Yeah. Come to the next one. Okay, one more question we'll ask. Sound waves in air are transverse, longitudinal, electromagnetic, and surface waves. In the air medium,
Longitudinal, sir.
sound wave longitudinal. Yes, correct. Sound waves are longitudinal waves because we've seen right now sound waves are examples of longitudinal waves. Which waves can be easily polarized? Sound wave, water wave, light wave, pressure wave.
Light wave.
Yeah, light waves can be polarized. Sound waves cannot be polarized, right? So, because light only we are using a polarized, you have to remember the polarized sunglasses are there, right? To keep our away from the light, to keep your eyes away from the light. So you have to remember the polarized can be done in the lights only. Yeah. Next, come to the speed of the sound. Right? The velocity, the distance traveled by a sound per unit time is given in a medium. Right? So velocity is nothing but the speed. Velocity is nothing but distance divided by time. How much time it taken, right? That is nothing but the velocity, distance by time. You see, it works different in the different region. If you take air, the sound speed is 331 meter per second. Right? If you take air, it is nothing but 331 or 331 to 340 meter per second if it is traveled in air at 0 degrees Celsius. If the temperature is rises to 20 degrees Celsius, what happens? Automatically, the speed is also increasing to 343 meter per second. Right? What is the normal temperature? The normal temperature might be 30 degrees Celsius or above that 20 degrees Celsius, right? So what is actually the speed of the what to say sound in that temperature of this one? is nothing but 343 meter per second. At 0 degrees Celsius only 331 meter per second, because it's taken as a medium. If it is in the water, the speed is very high, 1480. If it is in the steel, what happened? It is 5000 meter per second. The steel is the highest one. Steel is the highest one. Because I already told that it requires a medium. What happened? In the steel only the sound is maximum. That is 5000 meter per second is maximum. The next one is water, 1480 meter per second. The next one is the air at the certain temperature. So you have to remember that the sound waves increases in speed with increase in the temperature. With increase in the temperature. Here also humidity, whether it is a moisture, air or something, right? Humidity also increases. The speed will be increasing. That means in gases also increasing. The speed increases here also. In the temperature, the speed increases by 0.6 meter per second for every 1 degree Celsius. Whenever 1 degree Celsius increases, the speed of the sound is also increased by 0.6 meter per second. You have to remember that one. Might be it is also asked in some MCQs, right? For every 1 degree Celsius temperature rise, the sound is speed is increased by 0.6 meter per second. Right? What are the factors affecting the speed? Right? It's nothing but density. Right? Lower density, higher speed. Higher density, lesser speed. That lower density means you can see in a gaseous state. In gaseous state, what happened? It is higher speed. High temperature, automatically high speed. More humidity. More humidity also rises. What happened? That time also the speed increases because air becomes less density. Air becomes, during the humidity state, the air becomes less density, automatically speed increases. Wherever the density is lower, right, the speed or sound is increasing. If you say pressure, right, no effect at constant temperature. No effect at constant temperature. If you take it as a pressure, at constant temperature, there is no effect. So sound can be traveled in vacuum?
No.
Yeah, in vacuum, sound cannot travel, right? So the speed of sound is independent of frequency. That depends upon the elasticity and the density of the medium. Elasticity and the density of the medium only, the sound can travel. You know that elasticity, which one is having more elasticity? We've seen that steel is having more elasticity. So steel, it can take the highest speed, right? Now come to the important. Now we say that the speed of sound is maximum in air, water, steel, vacuum. The speed of sound is maximum where? Air, water, steel, vacuum.
Steel.
Yeah, I already told that and seen some practical also. In steel only, the sound is maximum, that is 5000 meter per second. It's maximum. Okay, the speed of a sound in air increases with pressure, option 1, density, temperature, frequency. The speed of the sound in air increases with, I want to increase the speed of the sound in air. Yeah, temperature. The temperature increases, it is come to the first, right? Temperature increases, the speed of the sound is also increases. Yeah. Next one, I'll complete this side. Pitch, loudness, and quality. These are the three characteristics of sound, right? Pitch. Pitch is nothing but if you are talking to the man and woman voice, there is some frequency, right? Because every voice has a modulation. That is nothing but the pitch. Loudness means there is a speaker will be there. We are increasing and decreasing the amplitude, right? That is nothing but the rising loudness. Its quality is nothing but the waveform, right? Their frequency ranges, infrasonic waves is less than 20 hertz, right? The audible range 20 to 20,000 hertz. Then ultrasonic waves is nothing but the greater than 20,000 hertz, right? The remaining thing you will see in the next class. Tomorrow there is no class, right? Because the new year, right? We can see from the 2nd January next year, right? Happy New Year to all. Right? We'll see in the next class. Hello.
Thank you.
Happy New Year, sir.
Happy New Year. Yeah, okay, okay. Tomorrow is no class, right? We'll see it on 2nd January. Okay, thank you.
Thank you.
Thank you, sir.